welcome to What's Up Physics. My name is Aishwarya, and today our lesson is going to be about friction. Let's get into it. Okay, so we did talk about friction briefly in our Intro to Forces video, so I'm going to do a quick review of everything we learned. So what is friction? Well, friction is the resistance of motion between two surfaces. It's the force that allows you to walk, and the force that prevents your phone from sliding on endlessly if you slide it against the ground. There are two types of friction: static friction and kinetic friction. Static friction acts on an object when it's not yet in motion. Let's say you're trying to push a really heavy object, for example, a fridge. Initially, when you apply force to the fridge to push it, it won't move. That's because the static friction force of the ground and the fridge is matching your applied force to keep the fridge in place. The more you push, the more that static friction force will grow to match your push. This is until a certain threshold is reached, called the threshold of static friction. After this point, static friction can no longer hold the fridge in place, and so it starts to move. Then, kinetic friction comes into play. Kinetic friction acts on objects that are in motion, or that are sliding. That's a key word to remember. For example, if we go back to the phone example, kinetic friction is what makes your phone to come to rest after a few seconds if you slide it along the ground. Kinetic friction always acts opposite to the direction of the object's motion. That's a really key fact to remember. Next, we have mu. Mu is this Greek letter over here, and it represents the coefficient of friction. In other words, it measures the stickiness or roughness of two surfaces when they slide against each other. If we slid two blocks of ice against each other, mu would be super low because there isn't much friction between the two surfaces. Conversely, if we slid two slices of peanut butter bread against each other, mu would be super high. Mu doesn't have any units and usually is a number from 0 to 1, though sometimes it can go over 1 if friction between two surfaces is super duper high. For example, mu would be closer to 0 if you're sliding on ice and closer to 1 if you're sliding on sticky, crunchy peanut butter. There are two different types of mu to measure coefficients of the two different types of friction: kinetic and static. Finally, we have the friction equation over here. It's pretty self-explanatory. It measures the amount of friction an object is experiencing based on the normal force on that object and the coefficient of friction between the object and the surface it's sliding against. For static friction, the equation measures the threshold, or the maximum amount of friction an object can experience before it starts moving. Let's go over the factors that affect the amount of friction force on an object. The first one is normal force, or perceived weight. Try this. Take a book and drag it along a table. Take note of how much you have to pull to get the book to start moving, and how dragging the book feels. Then, take 2 to 3 more books and stack them on top. Now, pull a stack of books across the same table, which you want to pull the book at the bottom of the stack, and don't try to push or touch any of the other books. You should be able to feel the difference in pulling the heavier stack. It takes a little more force to get the books to start moving, and the resistance to moving them across the table is greater. In other words, both static and kinetic friction are greater on the stack of books. This is because the stack experiences a greater normal force than the singular book. The second factor that affects friction force is the measure of mu, or the coefficient of friction. For example, if you have a wood or tiled floor, try sliding across the floor with a pair of socks on. Then, try sliding with your socks off. Can you feel the difference? It is easier to slide across the floor with your socks on because the measure of mu between the socks and the floor is less than the mu between your bare feet and the floor. The higher the mu is, the greater the friction force is. Finally, whether you are measuring static versus kinetic force on an object will affect the amount of frictional force you calculate. This is because the max amount of static friction an object experiences is always greater than the kinetic friction it experiences once it has started sliding. There's no easy way to demonstrate this, but I'm going to draw a graph to show this concept. Okay, so let's say over here on the x-axis we have applied force, and on the y-axis over here we have friction force. And for the purpose of tangibly understanding this concept, let's pretend we're trying to push a really heavy couch. As we apply force on the couch initially and we increase that applied force, it won't move immediately. That's because the static friction force rises to match our applied force. So the line on the graph then would look something like this. It'd be a linear line with a slope of 1 because the applied force and the friction force are matching each other. Let's take away this guy over here. Okay, so then at a certain point, we would hit our threshold static friction. Let's say that's over here. After this point, when we increase our applied force, the couch will start moving, and kinetic friction will be acting on it. No matter how much force we apply, the same amount of friction force will act on the couch. That force won't change in magnitude. But here's the key point. This amount of kinetic friction force is always going to be less than this maximum amount of static friction. So the graph would continue to look like this. It would dip down because our kinetic friction is less than that maximum static friction. And then it would continue in a horizontal line like this because that value will not change. So to sum this up real quick, if we draw a little split here, this side is our static friction. Over here is the maximum static friction, or the threshold point, that can be calculated using the friction equation. And then all over here is kinetic friction. Now, in the same line of reasoning, the coefficient of friction mu between the couch and the floor is going to be different between static mu and kinetic mu. Static mu is always going to be a little higher because the maximum static friction is greater than the kinetic friction once an object is moving. It's just a fact of life. So usually we'll be given two different values of mu, static mu and kinetic mu, for the same two surfaces. And this static mu is always going to be greater than this kinetic mu. So, depending on whether you're using the friction equation to calculate the max static friction or the kinetic friction on an object, you will get two different results. Now, I want to cover a common misconception that if you pull an object faster instead of slower across a surface, there is less friction force acting on it. In other words, the idea that speed affects the amount of friction on an object. This is not true. Regardless of how fast an object is moving on a surface, the properties of roughness between it and that surface do not change. The object's normal force does not change either. Hence, there is no way that pulling an object faster reduces the friction force on it. And speed isn't a variable in the friction equation, is it? So you can think about it that way. Now, finally, there's one last key idea. Remember that friction opposes the movement of an object. So let's say you have a box and it's being pulled by a tension force or pushed by an applied force. If that box is moving at a constant velocity, that must mean that friction is equal to that tension or applied force, because friction acts in the opposite direction of that force, and for a constant velocity to happen, all the forces need to balance out, or the net force needs to be 0. And if there are other forces acting on that object, then just make sure that you subtract friction from them. Okay, time for some example problems. Example number 1. A hockey puck is pushed across the ice and let go with an initial velocity of 21.5 meters per second. If the puck has a mass of 0.51 kg and mu k between the puck and the ice is 0.10, how long does the puck take to come to rest? Okay, so this is actually a callback to kinematics added with our knowledge of forces. Our problem is asking for time, and it gives us initial velocity. We also know final velocity, which must equal 0 since the puck comes to rest. So we have 2 of 3 variables to use our kinematics equations. What is the third variable we can find? We can find acceleration. We know the puck's mass, so we need to find the net force on it. So we should draw an FBD to organize our thoughts. We have the puck over here, and we know that the normal force and the gravity on it both cancel out. Our vertical forces are fine. Now, our problem says the puck was pushed and then let go. This means that as it is sliding, which is when we're drawing our FBD, or the time frame in which we're drawing our FBD, there's no applied force on the puck at all. Be careful of that. You don't want to accidentally draw on an applied force when our time frame is not talking about the push of the puck, but rather when the puck is sliding. However, we do know that there is friction force acting on the puck. That's what makes it come to rest. So we can draw that on this way. Let's say the puck is moving in this direction. Then the friction force is going to oppose that motion, so it's going to point to the left. And we can see that our friction force is our net force. So we can use the friction equation to calculate that amount of force, which is mu k times Fn. And then we can set that equal to ma because friction is our net force. So mu k is 0.10 times the normal force, which is the mass of the puck, times 10 to get its weight, and then the mass, which is 0.51, times A. And when you simplify this out, you get that A is 1 meters per second squared. Okay, so now we have our third kinematics variable, so we can use our first equation, Vf equals Vo, or initial velocity, plus At, and we can find T. So a quick side note, since we're slowing down, our acceleration points to behind us. So technically, acceleration is negative, which makes sense because friction is also opposing our motion. And even if you didn't figure this out immediately, it's okay, because if you solve, you will get T as a negative number if you put acceleration as positive. So then you can make the quick switch in your mind to acceleration being negative. So we have our final velocity, which is 0, initial velocity, which is 21.5, plus our acceleration, which is negative 1, times T, and this gives us that T is 21.5 seconds. Example number 2. If the 50 kg skier is sliding down a slope and the coefficient of friction between his skis and the snow is 0.20, what angle does the slope need to be for the skier to move at a constant speed? Okay, so we know that a constant speed means that there's no net force on the skier. Let's draw an FBD of the situation. So we have a slope like this, and this angle theta is what we're trying to find. Now let's say this dot is a skier. We can draw the skier's weight immediately and split that into components. We have FGX here and then FGY over here. Now we know that the normal force of the incline on the skier cancels out FGY. For this skier to have no net force, something needs to be canceling out FGX. That something is friction. We're going to have friction force pointing this way, which if the skier is moving down the slope, he's moving like that direction. So friction, it makes sense to be pointing the other way away from that. Okay, so let's set FGX and friction equal to each other. Then we can rewrite each one in terms of the values we know, namely Fg and mu, and also theta, which is what we're trying to find. So we have Fk is equal to Fg. Now we know that kinetic friction is equal to mu k times Fn. And we know that, this needs to be FGX. We know that FGX is the x component of the weight. So FGX is equal to the weight sine theta. And then we know that Fn is going to be equal to the y component of the weight. So it's going to be Fg cos theta. And then we're going to have this. Alright, so even if we're technically given Fg, or at least we can calculate it because we know the skier's mass, we can honestly just get rid of Fg right here because it's on both sides of the equation. So it simplifies what we're trying to solve. Now, to isolate mu k, I'm going to divide by cos, so we end up with sine theta divided by cos theta. And if you guys don't know, this is actually just equal to tan theta. And this is a common trigonometric rule, but in case you don't know that this is true, I'll do a quick explanation why. So it all comes down to what the side ratios of these trig functions represent. We know that sine represents opposite over hypotenuse, and then we're dividing that by cos, which is adjacent over hypotenuse. Rewriting this, we have opposite over hypotenuse times hypotenuse over adjacent. If we cancel out these hypotenuses, we're left with opposite over adjacent, which is the side ratios for the tan function. So that's why mu k is equal to tan theta. Now, if we plug in the value for mu k and we do some inverse trig, we have that 0.20, which is mu k. If we take the tan inverse of that, that is going to equal theta. And calculating that, we get that theta is equal to 11 degrees. And make sure you're in degree mode. Example number 3. Mariah is walking her dog in a park. When she takes a step, what is the correct explanation for why she is propelled forward? A. The normal force of the ground on Mariah pushes her forwards. B. The force of friction Mariah exerts on the ground moves her forward. C. The friction force of the ground on Mariah pushes her forward. D. The ground exerts an applied force on Mariah when she steps, pushing her forwards. Okay, so let's discuss each of these answer choices. Choice A talks about the normal force of the ground pushing Mariah forwards. we know that normal force is what keeps us from accelerating into the ground. In other words, the normal force is pushing Mariah up, not forwards. So, this choice is slightly incorrect because it's not what is allowing Mariah to move horizontally. Choice B should be ruled out immediately. That's because it is talking about a force that Mariah exerts on the ground. A force that she's exerting on another object has no impact on her own movement. It needs to be a force that is exerted on Mariah that propels her forwards. This leaves choices C and D. And this is where it gets a little confusing. It might be tempting to think that the ground is exerting an applied force to push us forward, or to push Mariah forward. But to be able to walk at all, we need to be able to grip the ground. In other words, when our foot steps, it needs to be able to push off the ground. And it can't do that if it just slides backwards past the ground. Can you see what I'm getting at? The key force that allows us to take a step is friction. The static friction between our foot and the ground makes it so that we don't slip and slide against the ground, which wouldn't allow us to take an actual step. Imagine if you poured a bunch of oil on the ground and then tried to walk forward in that oil. It would be very hard to cover any actual ground or walk forward because there would be very little friction between our foot and the oil, meaning we would slide against the oil instead of having any footing to walk. So to sum it up, the ground does push on Mariah and allow her to walk forward. However, the force that pushes Mariah is classified as friction and not an applied force because friction allows the grip for her to be able to take a step at all instead of just sliding against the ground. So, answer choice C is the correct answer. Example number 4. Mariah is pulling a wagon up at an angle on a rough sidewalk. If she increases that angle, how does that affect the value of kinetic friction on the wagon? Now remember, rough is a keyword for a surface that has friction. So in this scenario, what is the change of the pull angle doing? If Mariah is pulling up on the box at an angle that is not horizontal, which she is doing in this scenario, the normal force pushing up on that box will decrease. And I'll draw a quick FBD to show this. So here we have the box's weight, and let's say Mariah pulls a wagon handle with an applied force, and we can divide this into components, FAX and FAY. This FAY decreases the amount of normal force that the ground applies on the wagon. Remember, this is because with Mariah's slightly upwards pull, the ground doesn't have to push up on the wagon as much to keep it from accelerating into the earth. And of course, we also have a friction force over here, FFK. So the more of an angle Mariah pulls the box at, the more the normal force will decrease. And I'll show this over here by drawing another FBD where the angle of the pull is greater. So if we, again, divide this into components, this theta over here is greater than this theta. And what this does is that this increases this FAY over here, meaning the normal force will decrease even further. Sorry, that does not look like much of a decrease from the previous FBD, but it will be less. Now, what does that decrease due to the friction force over here? Well, let's look at the friction equation. We know that FFK is equal to mu k times Fn. Friction and normal force are directly proportional. In other words, the less the normal force, the less the frictional force. So, Mariah increasing the angle of her pull has the effect of lowering the friction force on the wagon. Example number 5. The two identical blocks shown below are at rest. Is the coefficient of static friction between the block and the table A, less than 0.5, B, between 0.5 and 1.0, or C, 1.0 or greater? Okay, so let's start by drawing on all the forces. Since the system is at rest, there should be no net force on the system at all. In other words, the sum of the forces on each block must be 0. Since the two blocks are identical, they will have the same magnitude of weight. So I'm going to draw on that FG over here. And those two FGs are equal. Then, looking at the hanging block, for it to be at rest, the tension force pulling up on the block must be equal to its weight. So there we have a tension force, and these two are going to be equal. Tension force in a string is constant throughout, assuming it's an ideal string, which it will be on the AP test. So the same magnitude of tension force is pulling on the block on the table to its right. So we have a tension force here, and that's going to be equal to this tension force. Sorry if it looks a little bit off, but assume that they're all equal in magnitude. Now finally, for the block on the table, for it to be at rest, the static friction force acting on it to the left must be equal to this tension force that's pulling on it to the left. So we're going to draw that on here. And note that since this static friction force is equal to the tension force and the tension force is equal to the weight of each box, the static friction force is also equal to the weight of each box. And finally, we need to draw a normal force on this table block over here that's equal to its weight. So basically, all the forces at play in this system are all equal to each other in magnitude. Okay, so now let's write down our friction equation. We have that FFS is equal to mu S times Fn. Now, we don't have any real numbers, but let's think about our goal real quick, to find mu. If we look at our equation, we can see that really, mu is just the ratio of friction force to normal force. We don't need to know the actual values of these forces, we just need to know how they're related. We just established that the static friction force on the table block equals in magnitude to the block's weight. We also know that the block's normal force is equal to the block's weight. In other words, FFS and Fn equal each other. So if we cancel them out in our equation, we get this. We get that 1 is equal to mu s. So this fits on the third answer choice, C. But how do we justify the greater than 1.0 part of this answer choice? Well, if you remember, the friction equation calculates the maximum possible static friction, or the threshold. Technically, the static friction could be less than this amount. It just can't go past it. So to incorporate this reasoning into our work, we can rewrite our static friction equation to look like this. FFS is less than or equal to mu s times Fn. Our block that's resting on the table isn't necessarily at the maximum static friction point just yet. For example, if a light added force pulls on the string over here, it could potentially still stay at rest because there's still a ways to go before the block hits the max static friction point. So in reality, this second equation here with the inequality is the correct one for our situation. Since we know that right now, static friction and normal force are at a 1-to-1 ratio, if we cancel those out like before, we get this. 1 is less than or equal to mu s. Or in other words, mu s is going to be 1.0 or greater. Example number 6. 2 stacked boxes are sliding along a rough surface. Below, the coefficients of friction between the boxes and between the system and the floor are given. Part A. What is the maximum force F that can be applied to the bottom box before the system starts moving against the floor? Okay, so this sounds like static friction. Remember, the static friction force of the ground on the bottom box will continue to match the applied force until the threshold point, or the maximum applied force that static friction can match. Until then, it will be at rest, which after that, it'll start to move. So we're just trying to find that maximum force. We have our friction equation. FFS is equal to mu s times Fn. The mu is going to be the coefficient of static friction between the ground and the box. So it's going to be this value over here. And remember, mu is just measuring the stickiness between the two touching surfaces. Only the ground and the bottom box are touching, so we only need to take their mu into account. Now, the normal force won't just equal the weight of the bottom box. It must equal the weights of both boxes added together, because the applied force is trying to move both boxes, and the static friction is stopping both boxes. And also, both boxes are pushing or weighing down on the ground collectively, so for them not to accelerate into the ground has to push up with extra force to account for the 5 kg box's weight on top of the 10 kgs. So now, we can solve for the threshold of static friction using our equation. FFS is equal to the mu, which is 0.25, times the normal force, which is going to be the weights of the mass of both boxes added together, so 15 times 10. Okay, and this gives us 37.5 newtons. Example number 6. Part B. What is the maximum force that can be applied to the bottom box before the top box slips and starts to slide? Okay, this problem is pretty complicated, so we're going to break it down by just isolating the top box first and drawing an FBD of it. So we can draw on our gravity and normal forces, Fg and Fn. Now here's where students make the biggest mistake. You might draw an applied force on the right, like this, and a friction force on the left, like this. However, this FBD is incorrect. Let's examine why. The hardest part to understand is that there is not an applied force acting on the top box. Yes, there is an applied force acting on the system of boxes as a whole, but it is being applied specifically to the top-bottom box. When we isolate the top box by itself, there is no applied force pushing it forward. So we can erase the FA. But then our FBD looks like this. Friction force pointing to the left, and then we have gravity and normal force. Now, the problem with this is that we know our box is accelerating to the right, at least when it's still on top of the bottom box. But in this scenario, the net force is pointing to the left. That can't be possible. So, the next idea to understand is that friction is not pointing to the left. It's pointing to the right. This might be weird because generally, friction is acting opposite the motion of an object. But try actually imagining the situation of stacked boxes sliding. If we push the bottom box super hard to the right, the top box might slide off to the left. In fact, you can try this at home. Grab any object, like a book, and stack a smaller object on it. When you pull the bottom object with enough force, the top object slides off in the other direction. What this means is, until the top box starts sliding, static friction is what is holding it in place. This is because the top box is at rest relative to the surface it's on, or the bottom box. Sure, the top box is moving relative to the ground because it's being carried by the bottom box, but the top box itself is not moving around on the surface of the bottom box, meaning static friction is holding it in place. Specifically, this static friction points to the right because it's resisting the motion of sliding off to the left, which is exactly what happens when the static friction threshold is overcome. So, a quick side note. While kinetic friction does act opposite the motion of the object, that's not always the case with static friction. So the correct FBD of the top box looks like this. We have static friction pointing to the right, and then gravity and normal force. This also makes sense now because the F net of the box is pointing to the right, which is the direction that the system accelerates. Now, where to go from here? Well, we need to calculate the maximum static friction force the top box can experience before it starts to slide. Then, we need to use that information to somehow figure out what the applied force on the bottom box needs to be in order to cause that maximum static friction. Well, what is the common link between the two boxes? They're both going to have the same acceleration, at least until the point that the top box starts to slide, because they are a connected system. We know that the static friction force on the top box is its F net. So, we can use the second equation to find the top box's acceleration when it is experiencing that threshold friction before it starts to slip. Then, we can apply the second law on the bottom box to find the applied force needed to cause that acceleration. So, we can calculate the maximum static friction force on the top box using the friction equation. FFS is mu S Fn, which equals this mu value right here, 0.5, times the normal force on the box, which is its mass times 10, and that gives us 25 newtons. Then we're going to set this value equal to ma of the top box to find its acceleration at this threshold friction, because remember, this static friction is the net force on the top box. So 25 is equal to ma. We know that the mass of the box is 5, so the acceleration when the box has this maximum static friction is 5 meters per second squared. Now finally, we can use second law to find the applied force that is needed to cause the bottom box to accelerate at this rate. We can't forget to subtract kinetic friction, calculated by mu k between the box and the ground, from the applied force, because the bottom box is moving at this point. In addition, our mass needs to be the addition of the top box and the bottom box's masses, because the top box is still on the bottom box at this point. So, this is for the bottom box, we have F net equals ma. F net is going to equal to minus FFK, and that equals ma. So FA minus, and you can't really see here probably, but the mu k between the bottom box and the floor is 0.20. So mu k times Fn, which is again going to be the addition of both the box's weights times 10, and then that's going to equal the mass, which is the addition of the two boxes' masses, times 5. Alright, and then when we simplify this all out, we get that FA is equal to 105 newtons. So there's our answer. The big takeaways from this problem is understanding that the FBD for the top box, and also remembering that the acceleration of a system is equal to the acceleration of its parts. I also want to talk about a common misconception real quick. The idea that the applied force on the bottom box should be equal in magnitude to the maximum static friction on the top box in order to cause that maximum static friction. As we can see here, that did not turn out to be the case. To cause the maximum static friction of 25 newtons, our bottom box needed to be pushed with an applied force of 105 newtons of force. So the only correct way to calculate this applied force is to use F equals ma and use acceleration as a common link between the two boxes. Example number 6, part C. If the applied force on the bottom box increases to 120 newtons, what is the acceleration of each box? So we determined in the previous problem that if the applied force is greater than 105 newtons, then the top box will start sliding. So at this point, the top box will be sliding to the left on top of the bottom box as the bottom box continues to move to the right. Be careful though. This does not necessarily mean that the two boxes' accelerations are pointing in opposite directions. Although the top box is moving to the left on the surface of the bottom box relative to the ground, it is still being carried to the right. The only difference is that, now that the top box is sliding, the bottom and top boxes no longer have the same acceleration. We can visualize this concept by drawing an FBD for each box. For the top box, we can draw on the weight and normal forces as usual. Now, the key idea is that since it's sliding, there is no more static friction acting on the box. It's kinetic now. Kinetic friction will oppose the motion of the box, so it will point to the right, because the box is going to be, that's kinetic. The box is going to be sliding to the left, like this. Now, the kinetic friction force is our net force, and it points to the right. Again, this might seem weird because the top box is sliding to the left. But remember, as long as it is still on the bottom box, it's still being carried to the right. Its overall acceleration is still to the right. Originally, static friction was the force that kept the top box on the bottom, meaning the two had the same acceleration. After that threshold was crossed, the static friction was replaced by a smaller magnitude of kinetic friction. And since kinetic friction can't keep the top on the bottom, the top started sliding, and thus its acceleration is lower than the bottom box. However, kinetic friction is what is keeping the top from sliding off the bottom, or in other words, it is what is keeping the top box accelerating to the right, which comes back to our FBD and how FFK is the net force pointing to the right on the top box. This is a little hard to understand. It's probably going to be the most complicated part of this lesson. Okay, now for the bottom box's FBD. So we can draw on its weight over here, and then the applied force of the top box's weight acting down on it. To match this, our normal force will increase to equal the weights of the two boxes. Next, we also have the applied force pushing it to the right, Fa, and we have kinetic force acting on it to the left, kinetic friction force. Now, there's one more force acting on this bottom box. As the top box slides, it applies a force to the left on the bottom box, like this. In other words, as it slides, it opposes the motion of the bottom box and slows it down a little. This force is equal in magnitude to the friction force the bottom box exerts on the top box. This is actually a third law concept. Each box applies an equal but opposite force on the other. Don't worry about understanding this now. We will cover it in depth in our third law video. It's just important to understand that the top box exerts a force on the bottom box that is equal in magnitude to the kinetic friction on the top box. So I'm going to draw this on over here, and I'm going to label it F top on bottom, just so that we know what that is. So the net force on this bottom box is this applied force minus the kinetic friction force minus this F top on bottom. Okay. So great, now that we know the net force on each box, we can apply numbers and solve for each box's acceleration. Let's do the top box over here. It's a lot simpler. F of k is equal to F net. So mu, which is this kinetic mu now between the two boxes, times Fn is going to equal to 5, which is the box's mass, times acceleration. And this yields an acceleration of 3 meters per second squared. The bottom box is going to be slightly more complicated. We know that F net is equal to Fa minus FFK minus F top on bottom. I'm just going to write top on B and that's going to equal to the mass times acceleration. All right, so we have 120, which is our applied force, minus the friction force, which is going to be 0.2, the kinetic mu between the ground and the bottom box, times the mass of both boxes, times 10 for the normal force. And then that's going to be also subtracted by 15 because that's the magnitude of this FFK that the bottom applies on the top, and the top is applying the same magnitude of force on the bottom but in the opposite direction. And then that's going to equal the mass of the bottom box, so 10 times A. And this is a little weird. This mass is not going to be 15 because the applied force is no longer pushing the top box at all. It's only pushing the bottom box since the system is not connected anymore. So we're just going to have a 10 there. And then when we calculate this, it brings us to 7.5 meters per second squared. This is a pretty complicated problem, so be sure to go back and rewatch or ask any questions in the comment section if you're having trouble understanding it. Example number 7. A box of mass 5 kg is dragged up a smooth incline of 30 degrees. On it sits a box of mass 2 kg at rest. The coefficient of static friction between the two boxes is 0.70. What is the maximum force that the bottom box can be dragged such that the top box stays at rest? Okay, so I'm going to draw a quick sketch of this problem first. We have our incline of 30 degrees. On that sits a bottom box and then the top box. And both of these are being pulled up the slope with the tension force. Okay, so the process of this problem should be similar to part B of the last one, except now we're on an incline. Since both objects are moving together, they've got to have the same acceleration. We can find that acceleration by using the net force of the top box, which we can calculate, and we can use the mass of the top box, which we have. Then we can use that acceleration to calculate the force the bottom box needs to be pulled at so that the whole system accelerates at that rate. So basically, like I said earlier, acceleration is the linking factor between both boxes. So let's start by drawing an FBD for the top box. We can draw FG and then split that into components since we're on a slope, FGY, FGX, and then this angle is 30 degrees. Next, we can draw normal force. This is the normal force that the bottom box exerts on the top box, and it's going to cancel out FGY. Okay, so what's keeping our top box in place from sliding down the slope to the left? That's static friction. Static friction holds the top box in place on top of the bottom box. Now remember, the net force of the whole system is pointing to the right, and so that means the net force of each individual box also must point to the right. We have this FGX over here, which is acting to the left, so the static friction on the top box must be greater than that FGX for the top box to have an F net pointing to the right. And in other words, the F net of the top box is going to equal to the static friction force minus the gravity, the x component of gravity, and we can set that equal to MA of the top box. Okay, so now we can plug in all the values we know and solve for A. To calculate the static friction force on the box, we know that the mu is 0.7, and then that's going to be multiplied by the normal force, which is 20, the weight of the box, cos 30. Because remember, the normal force on the box is equal to the y component of it. Okay, and then we're going to subtract the x component, so that is 20 sine 30 now, equals ma. So our mass is 2 kg and then acceleration. Now, when we isolate for A, we get that it is 1.062 meters per second squared. Okay, so now we have the acceleration of the whole system. We need to find what magnitude of tension force dragging the bottom box can accelerate the whole system at this rate. So let's find the F net on the system. We know that the x component of gravity must be pulling both boxes down the slope to the left. We also know that there's no friction between the bottom box and the slope because of this keyword smooth here. Smooth incline means that there's no friction. So FGX is the only force acting on the system to the left, and we know that FT is pulling it up to the right. Therefore, the net force on the system is going to equal to FT minus FGX of the system. Okay, and we'll set that equal to MA. Now, we're analyzing the motion of the system as a whole here, trying to find the pull that will accelerate the system as a whole at the acceleration we calculated. So our Fg must also equal the horizontal component of gravity acting on both boxes. So that's going to be 70, which is the weight of both boxes added together, sine 30. And then that's going to equal the mass of the system, 5 plus 2, times the acceleration, 1.062. Okay, and now if we isolate for Ft, we get that it is equal to 42.4 newtons. So this is the maximum force that can be exerted on the bottom box such that the top box won't slide off the opposite direction. Okay, thank you for sticking with me through this lesson. Next up is going to be Newton's third law. If you liked this video or you found it helpful, please be sure to like, subscribe, or share. Thank you so much and see you later. Bye!